Hey everybody, and welcome to my talk on sulfides, electrons, and the origin of life. I am Alexander Hollar, and I am an undergrad student studying chemical engineering at Arizona State University. For my talk, I'm going to be talking about sulfides here at the start, specifically iron sulfides. Sulfides are inorganic materials with a plethora of applications, from things such as high-energy density batteries to solar materials, and they can even be used as precursors for the synthesis of semiconductors. Iron sulfides today are commonly found in settings such as igneous rocks and even hydrothermal deposits, where they are hypothesized to have played a role in the first creation of life. A lesser known fact about iron sulfides is how big their importance in concrete integrity is. When iron sulfides in concrete aggregate exceeds about 1%, fractures and cracks will form as the concrete ages, which will effectively ruin the structural integrity of it. These cracks are accredited to how iron sulfides expand when they oxidize. Another instance in which an understanding of iron sulfides is needed is in understanding the phenomenon of acid mine drainage, which leads to a lowering in the pH level of ground and surface water. When exposed to the atmosphere, pyrite oxidizes to create iron sulfate monohydrate and sulfuric acid. The releasing of the sulfuric acid is the main culprit what causes this lower pH in ground and surface water. The reason why this phenomenon is called acid mine drainage is because this often takes place near copper mines, where when the miners are extracting the copper, they expose a lot of pyrite to the atmosphere, as pyrite often coats these copper ores. So continuing, what makes metal sulfides unique when compared to metal oxides? Generally, oxides are more thermodynamically stable than their sulfide counterparts. This partly has to do with their lattice parameters and how sulfide lattice parameters will be larger than oxide ones. The main reason that the lattice parameters are different is due to how sulfur is a larger atom than oxygen. Another difference is in their bonding. Oxides commonly only have ionic bonding present, while sulfides will have a mix of ionic, covalent, and metallic bonds. This is where the differences in the properties of the two comes from. A final major difference between sulfides and oxides that I will discuss is in their electrons. Sulfides exhibit more electron delocalization compared to oxides, which allows for better electron transfer in electronics. Two examples of situations where this is the case is in batteries and solar materials. So continuing on to batteries. Iron sulfides today are being researched as a possible anode material inside lithium-ion batteries. The reason why sulfides are being researched as possible materials is accredited to their abundance in nature as well as their high theoretical specific energy. It is thought that iron sulfides as an anode material could have specific energies around 3 times more than standard lithium-ion batteries today. However, the practicality of iron sulfides being used is hindered by a high irreversible capacity loss during the first few charge and discharge cycles. Upon cycling the lithium through the anode multiple times, surface cracks will begin to show up from the immense expansion and shrinking that the structure undergoes when it absorbs and desorbs these lithium ions. These cracks limit the anode's ability to store and release ions, which hinders the amount of energy it can store after just a few cycles. Another reason the Coulombic efficiency is so low is due to the generation of polysulfides, which readily dissolve in organic electrolytes. This is a problem because in batteries commonly used today, the electrolyte is an organic electrolyte. When these polysulfides dissolve into the electrolyte, this reaction cannot be undone, and as such, those sulfides are then gone from the anode for that battery. This is an example of how competing reactions can hinder the life expectancy of a battery. To combat this issue of competing reactions, solid electrolytes have been investigated. However, a lot of research still needs to be done before solid-state batteries are made widely available to the public with sulfides as in the anode. Another electrical application of sulfides is in solar materials. Pyrite, for example, has an energy gap of 0.95 electron volts, while silicon has a slightly larger energy gap of 1.1 electron volts. The reason why it is so important that the energy gap is like silicon's is since the energy gap is what determines the theoretical efficiency of the solar panel, as well as determines how much energy is needed to knock an electron loose from that panel. The larger the energy gap that a material has, the more energy it takes to knock an electron loose. Because of this, panels which have too large of a gap will not be able to effectively get these electrons knocked from the photons. However, having a smaller energy gap isn't necessarily better either. When a photon hits a solar cell, its energy is transferred into the panel. This energy is then used to knock an electron loose. Any energy that is left over from the photon is then transformed into heat energy, which will heat up the panel. This is an issue for solar panels, since solar panels are less effective or less efficient at higher temperatures. This is why a smaller energy gap isn't necessarily a good thing. The effect of this difference in energy gap between pyrite and silicon actually has a large difference in their efficiencies. Pyrite has a theoretical efficiency of about 15 to 20%, which is 13% less than silicon's theoretical efficiency of 33%. However, despite all this, pyrite is still a strong contender for a solar material, especially when compared to other photoactive materials such as gallium arsenide or cadmium sulfide. When compared to these two, the production of pyrite is less toxic to the environment, and it's also much easier to prepare. Moving on, now I'm going to talk about sulfides and their role in the creation of life. Pyrite has been hypothesized to be one of the first energy sources for life on Earth. The reason why it is thought that it is one of the first energy sources is since energy can be given off from the oxidative formation of pyrite. This idea was pioneered partly by Gunther Buchtenschauser, who claimed that biomineralization of pyrite was present in the first organisms on Earth. This essentially means that the organisms would synthesize pyrite, which would give off energy that it could use. These oxidations might have been done on the surface of pyrite, which could help explain the path of reaction which these bacteria might have taken to generate the energy. William Martin and Michael Russell suggested that life might have formed inside hydrothermal vents, which supply an abundant amount of sulfide materials in which life could be metabolized. This claim supported Buchtenschauser's findings, since it provided a source in which the sulfides could be provided constantly. This proposal also solved issues correlating with the supply of carbon and other elements for the formation of organic compounds, as well as allowed reactions that are favored by higher temperatures. This proposal contrasts with the heterotrophic soup theory, however, which claims that organic compounds were synthesized before life was formed, and then in this broth of organic compounds, life was born and it used the compounds to survive and reproduce. Today, sulfate-reducing bacteria play a key role in some sedimentary environments and even mediate the formation of iron sulfide materials such as pyrite. In places such as mines, bacteria can accelerate the rate at which sulfides will oxidize, in turn increasing the rate at which acid mine drainage will happen. In other places, bacteria are key in the formation of metal sulfides such as pyrite. These bacteria will produce hydrogen sulfide, which will then react with iron ions to form pyrite, resulting in the bacteria gaining energy from this reaction. These sulfides that are oxidized by bacteria will often involve a direct oxidative attack or an indirect oxidative attack. A direct attack is when the bacteria will target the sulfide's crystal lattice, whereas an indirect attack involves the bacteria generating ferric sulfate, which will then chemically oxidize the sulfide. The difference between the two is the method in which the oxidation occurs. There are two different ways in which the bacteria can interact with sulfides and their environment. So to finish off my presentation, I would just like to say thank you to the National Science Foundation and PIRE for sponsoring me in the research this summer. And another special thanks to Alexandra Navrosky and Christina Lilova for offering me their knowledge and help with learning these tricky subjects and really helping me with this research this summer, especially with COVID-19 going on. It's been a real roller coaster for a lot of people. So it was nice to have their support throughout all this and their guidance. Thank you.